Hello everyone, my name is Andrew O'Brien. I'm going to be presenting a 2013 paper from DeepMind called Playing Atari with Deep Reinforcement Learning. And the key idea of the paper is that it sort of incorporates advances in deep learning into a reinforcement learning framework, then applies it to playing several Atari games. And the AI agent greatly outperforms according to several previous benchmarks. And I'm going to give you some background ideas that you're going to need to understand the paper right now. All right, so this is something many of you are probably familiar with, but just a quick overview on supervised learning. It's a kind of machine learning, and basically you've got arrays of feature variables x and output variables y, and you've got a data set of those pairings, and you've got some learner function that you want to predict y's from x's, and it's a function of those x's and some parameters theta. And how you do it is you've got some loss function L, which takes in the data set, the predictions made by your learner, and gives you a measure of loss, which is basically how badly your model is doing. So you want to minimize loss, and you do that by adjusting the parameters theta to make predictions that are more in line with the data set. And as an example, you could have a very simple learner would just be a linear equation, a line with parameters w and b. Right, so it takes an x and then predicts the linear output. You've got a loss function, mean squared error, which is just the sum of the squares of the difference between the output of your learner and the actual label in the data y. Takes the average of those. And then you could, a common way to maybe the canonical way to minimize the loss is through stochastic gradient descent. You get the gradient of your mean squared error or your loss function with respect to the parameters, and you adjust the parameters in the reverse of that direction, which is the direction of steepest descent. And you keep doing that over and over until you've got your loss function as low as possible. Now, a kind of related idea is this idea of deep learning and neural networks. And what neural networks really are, this sort of function that's really a composite of these other kinds of functions that we call layers. What a layer does is really it takes the input from a previous layer, passes it through a kind of linear combination, sort of wx plus b, and then takes that output and passes it through some nonlinear output function g, which is usually called an activation function. And deep learning is usually a neural net function with greater than 2 non-output layers. And what makes it so powerful is that sufficiently complicated neural networks can approximate any function. And they've really, driven, the boom in AI since about 2012. And again, another topic I'm sure a lot of you are already familiar with. And now we get to this reinforcement learning, which is, I think, going to be this week's learn about it to some extent this week in class. And the key idea is you've got some setup, which is sort of an agent, which is in some environment, and it's taking actions through time. So each time step t takes some action in the environment, and the environment returns some reward and some state information about what state the environment is in now. And you can think of an example like for the Mario assignment we had, where either the AI agent we built or a human is the agent. We're taking actions, in the Mario game. This is the game emulator, and we get back state information about the sort of pixels about what the state of the game is now, and rewards in terms of coins and things like that. And so what reinforcement wants to do is it wants to learn basically a policy, a mapping of situations and states to actions, and actions that to maximize a numerical reward. And sort of a formal way to explain, kind of the previous slide we saw is this thing of Markov decision process. It's a sort of a little complicated, but its key ideas are you've got some set of states, some set of actions per state, some model function which gives the probability of basically some action in some state taking you to some other state, and some reward function which gives you the expected reward of if you're in some state, you take some action, you get in some other state, what the expected reward from that transition is. And again, we're trying to learn policies which map state to actions. And the question is, okay, how do we do this then? right? Because this isn't the sort of same setup as a supervised learning from before. And first, we introduced the idea of return, which is, again, what we're kind of trying to maximize G sub t, and the idea is it's the sum of the sort of discounted future rewards. And the idea basically is the discounting reflects the idea that we often care about rewards far in the future, less than rewards in the present. So the sort of that gamma coefficient is between 0 and 1. And also this makes the return converge mathematically. A key notion that we use to start to come up with our sort of idea of a policy is oftentimes is this thing called a Q function. And what a Q function is, it's a function Q with respect to some policy pi that takes in a state S and a action A. And what it gives us is the expectation of the return if we were to take action A at time t in state S, and thereafter follow policy pi for the right until infinity, or until the game ends. And we can think of an upper bound kind of on Q as some function kind of Q star, which is the idea, imagine we were playing perfectly. So if we took some action A and state S and then played perfectly thereafter, what would our expected return be? And if we had that function, we could just construct a pi star, an optimal policy. It would just be argmax with respect to A of Q star, the action A and S that yields the maximum return. And if you look at the bottom bullet point there, that's an equation called one of the Bellman equations. And what they do is they characterize an optimal solution, right? In this case, an optimal Q star. And basically what it's just saying is that Q star equals the expected return, right? It's just saying the sum to, all future possible states, what's the probability of arriving in that state, times the expected reward there if you arrived in that state. And what this equation did, it sort of led into the idea of a possible algorithm for getting Q star, actually learning it. And it was called, the original algorithm is called a Q learning algorithm. And so the idea of the Q learning algorithm is that, you've got some random assignment for, QS of A, right? You've got some, let's say you have some table, right? Then you initialize all the QS of A values to randomly, right? Is there any way to then start learning better Q values? And there is. You just use that last equation, use it as a kind of update, right? So you take some action, you get some reward, and then you update your entry for S and A. And you do it, and the basic idea is you take the difference between sort of your current, you take something, you update it in a way that's proportional to the difference between your current value of S of A and this sort of target value, which is the reward you get for the action you took, and then your expected future return using, if you played optimally, using the current Q value you have. And basically the idea is if you kept taking actions and kept updating proportionally to that direction, you would eventually converge on Q star. If you played long enough, this algorithm will work. The problem is that the essay space is enormous for tons of games. Think of chess, think of checkers, think of Go, and particularly games like Go, where the action state space really is just enormous. It would take forever to converge on the optimal Q star values. So instead what we do is we try and approximate Q star, and we come up with some function, approximator function, which is a function of SA and some parameters W. And this basically leads us to the idea of Q learning. We're going to try and approximate Q star using a neural network, basically, in a deep learner. And that's the idea for the paper. And this is deep Q learning. Before showing you the formal algorithm, I'm just going to explain to you the key ideas. Up top, the truly fundamental innovations they made with this idea of experience replay and fixed Q targets. And so I'm going to explain those as we go down here. So first, you start off, you basically you've got some policy, some initial Q values, and you take action A sub t according to an epsilon greedy policy, right? So, epsilon is, like 0.05 or something. So 1 minus epsilon per, as a fraction of the time, you act according to Q, and then epsilon, fraction of the time, you act randomly. And then you get some data, right? You get this experience tuple which is basically the current state you were in, the action you were in, the reward you got for taking that action, and the successor state. You store that transition in a replay memory D, right? And then, over time, right, you're gonna, build up a lot of these transitions. And so what you do then is you sample random mini batches of transitions from D, and you compute Q-learning targets with respect to the old fixed parameters. So the idea is you kind of actually have two Q networks, two of these neural networks, sort of going at once. Not exactly, but the idea is that you've got one neural network which has the parameters W, we'll say W negative, frozen, right? And then one Q network which is using your most recent parameters, which is just W. And basically you kind of, and this is called fixed Q targeting. And the idea is that for your loss function, right, whose gradient you're going to use to make the updates, your sort of target value uses the old weights for a while, and after a certain period of time, you update the old weights with the new weights. And what both fixed Q targeting do, and this idea of using sample random mini batches, is they increase the chance that both your loss function and your weights are going to converge through training, right? One of the differences between data acquired in this way and data for traditional supervised learning is you have this assumption in traditional supervised learning called IID, which is uh, independent and identically distributed data. Those assumptions don't hold in reinforcement learning, right? The data you see, these SARS tuples, are correlated, right? Of course, one data instance is very much a function of the data you just saw. And so the idea of sort of not updating right away, but storing these experience tuples in D, and then of course, and freezing Q for a while. Those are the ideas, of course, of experience replay and fixed Q targeting. It helps a lot with convergence and makes the data more like independent and identically distributed data. All right, so then after you've computed your Q learning targets, you optimize the mean squared error between the Q network and the current Q network and the Q learning targets, which makes use of the Q network with the old weights. And there's your, again, that's the loss function, which is mean squared error. And you basically update the weights like we saw before, just using stochastic gradient descent. And we're going to see the algorithm formally written out. And again, just I'll quickly go through it. It's basically the ideas we saw before. You initialize this replay memory D to some capacity N. You initialize the action value Q with random weights, right? For each episode of the game, right? I1 through N, do the following. You basically just initialize your initial state and you pre-process the sequence. What they're talking about with the pre-processing there, that function of your state, is the idea that to make the processing better and smoother and basically go faster, they cropped the pixel images that they got for the Atari games, and they made them grayscale. And then for the time steps inside each episode, for t equals 1 to t, right? They select an action using basically epsilon greedy, right? It's epsilon, probably epsilon they selected randomly. Otherwise, right, they selected an action which was max with respect to your Q star approximated function. They executed the action in the emulator. You observe the reward and the new pixel image, right? You update your current, basically you update your current state. You pre-process the new state, store the transition, sample the random mini batches, and then you set Y, right? It's sort of, which is going to be right your target. So if you're in the final possible state, Target's just the reward, otherwise it's the reward plus gamma times the max A. Q as a function of your basically old weights. And then you sort of perform right now the gradient descent step, and then you loop back for the next t. And as I can say, it's using deep networks. It's a more sophisticated example of Q learning, and we're going to talk about the actual experiments they did using this algorithm on Atari. And they took 7 different Atari games. For their neural net, they used a CNN architecture. It was actually a fairly simple CNN, just 3 hidden layers. They used the same network architecture, learning algorithm, and hyperparameters for all 7 games to show that it was robust. For the algorithm isn't really suited for just one game, and it really can learn across different games. The only alteration they made was they altered the rewards to all negative rewards were -1, all positive rewards were 1, and neutral was 0. And that was somewhat to help learning across different games. And in order to speed up training, they only selected a new action on every kth frame, which was either 3 or 4 frames, depending on the game. And then for the other frames that weren't the kth frame, they just took the action that the most previous action decision decided on. And here are the results. And so you can see so what you've got here is basically how they compare their deep Q network to, if you look at the sort of top box of the 2 boxes, right? You've got how the deep Q network performed against a human expert, random play, and SARSA and contingency. And those are 2 reinforcement learning algorithms that had been used in the past. And so there you can see that, say for B-Rider, right, deep Q network basically crushes the other the kind of other learning algorithms. It still loses to the human expert though. For Breakout, it beats both the human expert and the other learning algorithms by a lot, as it does for Enduro, as it does for Pong, as it it doesn't beats the other learning algorithms for Q Starbird, still loses the human expert. Same for Sequest, same for S Invaders. And then if you look at the sort of kind of bottom there with the N neat best and HN neat pixels, those are just basically evolutionary algorithms for selection, and you can see that it for B-Rider beats them both easily, for Breakout beats them both easily, for 661 beats them both easily, for Pong beats them both easily, for Q Starbird beats them both easily, for Sequest beats them both easily. Doesn't for S for Space Invaders. And so kind of my opinion, the paper represents a landmark achievement in reinforcement learning, introduced this sort of revolutionary kind of deep Q learning. In particular, its idea of having a fixed Q network and experienced replay helped overcome correlations in the data that you were seeing, and helped achieve stable Q learning and stable loss function. I think that there's some criticisms would be, there's this open question of what about sort of these sort of non-virtual applications, sort of robots in the real world, right? Robots, you can't let it's much harder to have, robots learn by sort of spending tons and tons of time training. And also the non-visual data, can this be done with, learn from, sound or stuff, right? How dependent are you on the fact that you have this sort of, your data is basically pixels, as a sort of your state, using CNNs? What about, words and other forms of data? It's still unaddressed for this question. And that is my, again, so I thought it was a great paper, some open questions still, and thanks for listening.